Unit 3 Supplement, Indirect Proofs. Indirect proofs begin with the law of non-contradiction, which states that nothing can be both true and false in the same sense at the same time. Our entire logic system depends on this law that says, basically, P and not P is always false. For this reason, we sometimes call indirect proofs reductio ad absurdum, which means something like to reduce to absurdity. With this method, we prove that something is true by demonstrating that if that thing is false, a contradiction would be entailed. If not P entails a contradiction, any contradiction, say Q and not Q, then P must be true. This method proves the conclusion indirectly, hence the name. We assume the opposite of the conclusion. Then we show that a contradiction is entailed, and our conclusion is proved. Why do we use them? In life, well, we really argue this way. If someone shows you that something you believe entails a contradiction, you've got to think about it. Either your belief is wrong, their logic is wrong, or maybe some contradiction is actually true, though this last one isn't all that likely. In logic class, we use them both to mirror real life, and because indirect proofs are often easier. They always work. Since the conclusion is always true, its opposite always leads to a contradiction eventually. You'll usually be able to use simpler rules in an IP proof. Some systems rely on IP so much that they have far fewer rules than we do. But they do usually take more lines, and therefore sometimes more time to complete. Steps. First, assume anything. We'll call that X. It could be a sentence letter, it could be a whole sentence, it could be very long, though it does have to take exactly one line. Then we set it apart in brackets and conduct our proof just like we normally would with rules and citations. Step 3. We show that the assumption entails a contradiction. Just get to a line that states any contradiction like Y and not Y in that format. You'll be using conjunction a lot. Then we close the brackets. Not X is now a normal line in the proof. What does that look like with an actual proof to demonstrate on? Let's try with a very simple one. This one has only one premise. If A, then it's not the case that B or not B. Therefore, not A. Let's take a look at that premise. Especially this, it's not the case that B or not B. B or not B is a tautology. It's always true. So its opposite is a contradiction. So something that entails the contradiction must be false. In our first line, we're going to use De Morgan's to take that negated tautology, it's not the case that B or not B, and turn it into a very easy to see contradiction. So that becomes not B and not B. It's in exactly the right format that we need if we could get a modus ponens. So let's assume A. That's going to allow us to get a modus ponens after all. Notice that we've used brackets for line 3, and while we don't know what we're going to put for line 4, we know that it's going to depend on our assumption. So we've got a bracket right there in front of it as well. Our next line is that modus ponens, and it brings us to step 3. Show that the assumption entails a contradiction. It's not B and not B. Now, any old contradiction will do. This one is slightly more complicated than necessary. If we wanted, we could use double negation and get not B and B. But we don't need to. This is a contradiction all by itself. That's good enough. Close the brackets. Notice that there's no bracket there in line 5. And now we have not A, citing indirect proof, lines 3 through 4. Notice our citation. It's got a dash instead of a comma. This means that indirect proof covers all the lines in the brackets. Instead of saying that there's just one or two lines that are evidence to prove that our line is logically entailed, everything inside the brackets is working to do that. Those lines inside the brackets can't be cited from outside. After all, they depend on an assumption, A, that we just proved to be false. Now, even if we end up proving our assumption true, that would be a mistake in an indirect proof, but if we happen to do so, everything in the bracket still depends on an assumption. We can't use those. They're not logically entailed just by the premises. They're entailed by a combination of the premises and an assumption that we're not actually sure about. We can't use those lines outside the proof. We'll see more of that in the next example. Let's take a look at a proof that's quite a bit harder. Our first line, if it's not the case that x and y, then z and not y. Alright, second line, either y or if z then x. Conclusion, x. Well, this is a pretty messy looking proof with a very simple one-sentence letter conclusion. That makes it a great candidate for indirect proof. However, before we begin assuming things, setting them in brackets, and writing lines that we can't use outside those brackets, it's best to do any easy rule, or even any more complex rule that strikes us as being useful to do. So I'm going to do De Morgan's on line 1. Now it reads, if either not x or not y, then z and not y. Now if you caught on immediately as to why I did that, that's great. If you didn't, hopefully it'll become a little bit more obvious once we do make our assumption. After our first De Morgan's, I don't see anything else interesting or useful to do, so I'm going to go ahead and make my assumption, not x. When you're doing an indirect proof, the simplest way to do it is to assume the opposite of your conclusion. You don't have to, though. Every once in a while, there's good reason to assume something else. In this case, we'll do it the simple way and stick with not x. Now, we're going to set it in brackets and conduct our proof as normal. And what we're going to do is use addition. Here's why we did that De Morgan's. De Morgan's let us turn a negated ampersand into a disjunction. A disjunction with the opposite of our conclusion in it. Now we've got not x in line 3, and we've got not x in line 4. If we remember the way that the disjunction works, it's true if even one side of it's true. Once we've got our assumption, not x, on the board, we know that we should be able to get to z and not y with a modus ponens. The only trouble is the form doesn't match, even if we know that the logic does. That's why addition works. Addition feels like pulling a rabbit out of a hat. At least it does to me sometimes. But it's all based on the fact that a disjunction is true if even one side of it is true. So we're going to go ahead and add not y. Now modus ponens gets us z and not y, and simplification gets us z and not y separately. This is very much the conduct proof as normal part of our work here. But remember, any of these lines cannot end our proof, and they can't be cited outside of the brackets. We haven't proved that these things are entailed by the premises alone. They're entailed by a combination of the premises and the assumption of not x, which, is going to end up proved false. Now we'll do a disjunctive syllogism. Now that we've got not y, we can apply that to line 2 and get if z then x. Now I hope you're able to see where we're trying to go. We've got not x, line 4. We've got x as the antecedent of a conclusion, a conditional rather, in line 9. And we've got z in line 7. Z should lead us right to x. which should lead us to x and not x, which should let us close our bracket. Sure enough, modus ponens, lines 7 and 9, gets us x. And wait a minute. There's x in line 10. There's x in our conclusion. You might be tempted to stop the proof here, but we're in brackets. The proof is not done. We haven't proved x yet. Again, we're still working with the assumption. This is why it's really important for you to go to the trouble of actually using brackets when you work with assumptions. Not every system will demand that you do so, but ours does, and I will take points off your quiz if you don't use them. They're just like parentheses, in my opinion. They help keep straight what is supposed to go where. X is inside the brackets. It depends on our assumption that we're about to prove false. It can't conclude the proof. We're going to have to derive x in another way. And of course, we're almost there. Because we have x and not x, we can show that this assumption entails a contradiction. By the way, we could have used modus tollens on lines 4 and 9 and gotten not z, and used conjunction with line 7 to get z and not z. That would have been fine too. Any contradiction will work. If we could have found some way to get y and not y, that would have done the job as well. Now, we can close the brackets, now that we've found our contradiction. Notice that line 12 does not have a bracket. We've now got not x. The brackets are closed. All the lines in there can't be cited. They were used to prove line 12 by proving the assumption false, and they did that. Everything in there is all merely evidence for line 12, not x. And this proof is almost, but not quite done. For line 13, the only lines that we could cite are the premises, line 3, and line 12. But fortunately, line 12 is all we need. We just double negate it, get rid of those two not signs, and now line 13 matches our conclusion. You may somewhat frequently need to do one or two lines, often double negation, but sometimes something else, in order to finish your proof after you've done the indirect proof part of your work. And that should do it for how to do an indirect proof. We've seen how to make the assumption, how to use the brackets, and how to show that your assumption entails a contradiction.